Hello everyone, welcome to chapter 18, Planar Kinetics of a Rigid Body, Work and Energy. This module is going to discuss principle of work and energy. The objectives is first to develop the principle of work and energy. So basically, you should review the previous module if you are not familiar with how to get the work done by forces or even the kinetic energy of a rigid body undergoing either translational, rotational, or a combination of both. Then we want to apply the work and energy to rigid body problems involving force, velocity, and displacement. Quickly, this is something that I have discussed in the previous module. I'll go through it very quickly. For pure translation, you don't have any angular velocity, and therefore you end up with only half mvg squared. This is very straightforward. If you happen to have a rotation about a fixed axis, as shown in here, so this is fixed, then you know that there is a relation between the velocity and omega, that vg equals rg times omega. Therefore, the kinetic energy can be rewritten as half ig plus mrg squared multiplied by omega square, and this is what we call the parallel axis theorem. Now, another way of doing it is that if you happen to know the formula or expression for the mass moment of inertia I around point O of a fixed point of rotation, then you can directly write T as half I O omega square, and you do not have to include the velocity in this case. Okay, so you have the two options. This is the first one, this is your second option. Now, if your G point and O happens to be the same, meaning that, let's say I have a disk that is rotating around its own center of mass. Okay, therefore, point G and point O are the same, and in this case, this part is no longer valid because velocity of g becomes 0, and you end up with t equals half ig omega square. For general plane motion, where the center of mass is not the center of rotation and the center of rotation is not on your object as the previous slide, then t will equal to half mvg square plus half ig omega square. Now, regarding the work done by a force, this is exactly similar to particles. The work done by a force, the general expression is that it will equal to integral of f cosine theta ds. If the force happens to be constant, then this is much simpler and you don't need to carry out the integral. It's basically fc cosine theta, if there is an angle, times the distance s. For the weight, it is minus W delta y, where delta y is basically y2 minus y1. So it is the final position minus the initial position. And there is a minus W. Don't forget the minus outside of this. For spring force, again, one of the main sources of confusion to students, it is always minus, then open a bracket, half ks2 minus half ks1 square. Half ks2 square minus half ks1 square. What is s2? It is basically the length at that position, which is position 2, minus the unstretched length. What is s1? It is the current length at position 1 minus the unstretched length. The confusion comes that some problems will give you the amount of compression directly. We'll say that at this position, the spring is compressed or stretched by amount of 0.5. Then that is your S value directly. Some problems will give you that the spring has an unstretched length of, let's say, 1 centimeters or 1 meters. And at this location, you have to find the length. So it becomes 1.5, for example. Then you have to subtract them and get the S value. Now, the principle of work and energy is something that you should be familiar with by now. It is T1 plus summation of the work done between 1 and 2 equals to T2. Now, keep in mind that this is a scalar equation, so it solves for only one unknown. Okay, it does not solve more than one unknown, so this is a scalar equation that we use. So start with the first problem. Gear A has a mass of 10 kilograms and a radius of gyration of 200 millimeters. Gear B has a mass of 3 kilograms and a radius of gyration of 80 millimeters. The system is at rest when a couple moment of magnitude 6 Newton meter is applied to gear B. Neglecting friction, find the number of revolutions executed by gear B before its angular velocity reaches 62.8 radians per second, and then find the tangential force between the two gears. So to find the number of revolutions, therefore I have velocities, I have forces, and I have revolutions, which is angular displacement. Then this is a work and energy type of problem. So let's start first with finding all the parameters and unknowns that I need in this problem. At this point, okay, at this point that I'm showing here, I know that SA should equal to SB. I know that VA should equal to VB as well. Therefore, I can say that VA, which equals to RA omega A, should equal to VB, which is basically RB omega B. Now RA is known, RB is known, omega B is known. I need omega A. Therefore, I can say that omega A should equal to RB over RA times omega B, which is 100 over 250 times 62.8, and this will give me 25.1 radians per second. Okay. Also, I can write the mass moment of inertias to do them. I am given the radius of gyration, which is used as MA KA square, and the mass of A is 10. And the radius of gyration for A was given as 200 millimeters, so it is 0.2 meter square. This gives me 0.4 kilogram meter square. Same thing for B. I will do this one quickly. So it is MB KB square. Mass of B was given as 3 kilograms, and radius of gyration was given as 80 millimeters, so it becomes 0.8 meter. Then you have a square, and this becomes 0.0192 kilogram meter square. Now I have everything ready to start doing all my calculations. So to do the principle of work and energy, let's start with every term separately. And this is a practice that I always suggest to students. Never try to solve the problem directly at once. Do all the terms separately, then add them at the end. So I have T1 starting from rest equals to 0. T2, now let me analyze this motion. I have two gears, each one is rotating around its own center of mass. Therefore, I have only angular velocities to account for. There is no velocities. So it's going to be half IA omega A square plus half IB omega B square. And I have everything ready, so it's going to be half. This is equal to 0.4 times 25.1 square. And for B, you have half. IB was 0.0192 multiplied by 62.8 square. And this gives me kinetic energy equals 163.9 joules. Okay, so I have the two. Now I need to find the work done. So let's look at the forces acting on this problem. If you have the two gears, I have the couple moment M. I have weight of B, and I have weight of A. Now, keep in mind that two tangential forces are equal in magnitude, opposite in direction, so they cancel. And the weight is applied to the center of mass, which does not move, so they do not give me any work. The only thing that is left is the moment. Therefore, the work done between 1 and 2 should equal to m multiplied by the rotations of B. Okay? And since this is the unknown, it's going to be m, which is 6 newtons meter times theta B. So everything is known. Let me apply now, except for theta. So apply the theory. Should equal to T2. T1, remember, was 0 plus 6 theta B should equal to 163.9. Everything is known except for theta. So this gives me theta B equals to 27.32 radians. And you can also convert this to revolutions, so it becomes 4.35 revolutions. And this is the first part of the problem. So let's go to the second part. Now it says, find the tangential force which gear B exerts on gear A. Now, from the previous part, remember I told you that the tangential forces here are equal in magnitude, opposite in direction, so they cancel. In order to find this force, then I need to separate A and B and solve one of them individually. So I'm going to do gear A alone. So at gear A, I have the pin reactions, which they do not give me any work. I have the weight, which also is not going to give me work. And I have this force applied at this point, which does move, so there will be work done by this point. So I'm going to start all the calculations. Start again, everything should be written separately. Starting from rest, T1 is 0. T2, I have only rotation, so it's going to be half IA omega A squared, which will equal to half 0.4 multiplied by, fix this, so we have half of 0.4 multiplied by 25.1, and this should give me the kinetic energy to be 126 joules. Now, let's look at the work done by the force F. Okay, work done between 1 and 2. So it equals to F times SA. Now, I don't know what is SA, but I can write it in terms of theta. So I can write it F equals to RA theta A. Now, I don't know theta A. I know theta B from the previous part. And if you remember that I also know that SA should equal to SB. So basically, I can also rewrite this as F RB theta B. As simple as that. So it can be written as RB equals to 0.1. Theta B, we just calculated it to be 27.3 radians. And this is multiplied by F. So this equals to 2.73 F. So everything is known now. T plus work done equals to T2. This is 0. This is 2.73 F. And this is 126. Solving this will give you the force F to be equal to 46.2 Newton. And this is from B acting on A, so it is the one in this direction. And this solves the problem. Now, I would suggest, just, for the sake of it, that a good practice in this problem will be that instead of doing gear A, do gear B. Okay? And you will have the force F acting in this direction, and you'll have also the work done by the moment M. So solve it for this case, and you should get F equals to 46.2 Newton but the only difference is that it's going to be in the opposite direction. So just solve it and make sure that you get the same value. Now, the second problem that we have, if corner A of the 60 kilogram plate is subjected to a vertical force 500 Newton and the plate is released from rest when theta equals 0, find the angular velocity of the plate when theta equals 45. Okay, now to start off, the first thing you need to do is that let's look at the two positions of this problem to analyze the velocities. At position 1, theta was 0, so it was something like this. And just to remind you that this is theta, so it is the angle with the horizontal. So it was 0, so it was something like this. This is the velocity of the center of mass, it was 0. And omega, if this is moving in this direction, so omega should be something like this. So omega in this problem is also 0. There is no movement. Now when it reaches 45, okay, so this will keep moving upward. This will keep moving to the left until it reaches angle of 45. Then it's going to look something like this. Okay. Now, to analyze the velocities, and this is a very important aspect of the problem, is to organize everything to understand all the terminologies and all the velocities. Now, I know that this point was moving. This is point B. So VB2 was moving like this. And this point A was moving like this, VA2. Now, if you remember, from the instantaneous center of zero velocity, how would you find the center of rotation for this problem? That VB2 is acting horizontally, so you can take the perpendicular to it. Velocity of A is acting upward, so perpendicular to it is like this. So this point becomes my IC. Okay, therefore, the velocity of this point, VG2, should equal to R IC omega 2. Okay, and it's going to act somewhere like this. Okay, so this is what we need to analyze first. So this is what I needed to get clear. Now let's write everything that we have. So T1, everything at rest, so it's equal to 0. For T2, this is a general plane motion, so I have a velocity and I have omega, and the problem asks you to find omega, find the angular velocity. Therefore, instead of using Vg2 as an unknown, I'm going to relate it with omega 2. So I know that Vg2 should equal to omega 2 and then Rg with the IC, which equals to, omega is unknown, and what is Rg to the IC? So this angle is 45, so this angle is also 45. This length is 1. All of these lengths are 1. Okay, so this velocity, this distance, this is the R, so it's going to be 1, and this is also 45. 1 cosine 45. This is the 1. This is the angle, so this becomes 1 cosine 45. So it's going to be 1 cosine 45 omega 2, which equals to 0.7071 omega 2. And also, let me compute the mass moment of inertia, Ig, for a rectangle like this. It is 1 over 12. Okay, so I will compute Ig, so 1 over 12 mass m, then a square plus b square. Now it happens that In my case, it's a square, so they have the same length. So it's going to be 1 over 12, and the mass is 60. And then A and B are 1 and 1. So it's going to be 1 square plus 1 square. And this will give me 10 kilogram meter square. Okay, so always don't forget to write the units when you are computing any value. Okay, now everything is there, so I can write T2 now. So T2, remember this is general plane motion, so it's going to have first half m VG2 square for the center of mass plus half IG omega 2 square. So this equals to half 60, and then convert Vg to omega, so it's going to be 0.7071 multiplied by omega 2 square plus half multiplied by Ig, which is 10 omega 2 square. Compute all of these, we can get the value, which almost equals to 20 omega 2 square. Okay. Now, we need to do the work done by the forces. So again, let's look at the problem. First of all, position 1, I'm going to repeat these two positions, 1 and 2. I'm going to look at the forces acting on it. So, position 1, it was something like this. This is the weight. Okay, and this is where the force P was applied. And this is 1. And this is 0.5. At position 2, I have something like this. Okay, so always draw things roughly so you can analyze things and understand how do they look. I'm just gonna draw it more properly. Okay, so what do I have now? In this case, this is my force P that is applied, and the center of mass is going to be somewhere in here. So this is my W. Now, these are the only two forces that we have. If you look at the problem, we have the weight acting downward, and I have the force P that is given. So let's look at these two. Basically, what I need to do is look at the amount of motion that they moved. So first of all, let's look at SP. How much did it move? To make it easy for you, let's pick a reference. So let's take that this is my reference. Here, the distance, I'm going to see the distance between this point of the force P and the reference. And also, again, this is the ground. So this is the reference. And this is P. So I'm going to take the distance between P and the reference and subtract it between the two cases. So for the first one, okay, remember that this is 1, these lengths are 1, and this angle is 45, okay, and that's what they have. So let's look at P. Now, this part from here to here, so this one is 1 cosine 45. And this one from here to this point is also 1 cosine 45. This total becomes 2 cosine 45, the distance between P and the reference. So this is the final position minus the initial distance in the initial position, so which is basically 1. So minus 1. So this is the distance that I have in the first for the load P, which equals to 0.4142 meters. Now I'll do the same thing for the weight. So SW will equal to, let's look at the first case, the position 2 first. So the distance, this is 1, and this angle is 45. So this distance from here to here is 1 cosine 45. Minus the distance from W and the reference is 0.5. So it's minus 0.5. and this equals 2.2071 meters. So I have the distances with me and they are clear. So now I can calculate the work done by each one. So the work done by the load P equals 2. Now, if you want to know it is positive or negative work, look at the forces. The center of mass moved upward for A, and also the center of mass, as this moved, changed to be positive. Okay, because it was like this, and then as it moved, it became like this. So the center of mass was in this line, and now it is in this line. So this is 1, this is 2. So it moved upward. So P will give me positive work because it moved upward and P is acting upward. The weight will give me negative work because the center of mass moved upward while the weight is acting downward. So UP will equal to P times SP. So this equals to 500 multiplied by 0.4142, and this should equal to 207.11 joules. The work done by the weight, this case is going to be minus W S W, and this will equal to minus the mass 60 times gravity 9.81 times SW, which is 0.2071, and this should equal to minus 121.9 joules. Okay, so apply now principle of work and energy. Everything is ready to be plugged into the equation. Remember, T1 was 0 plus the work done is 207.11 minus 121.9, and this should equal to T2, which is 20 omega 2 squared. Solving this will give me omega 2 equals to 2.06 radians per second. And this solves the problem for us. Now, the good thing about this example is that it is good to practice how to analyze the figures. For example, when I did the velocities, draw position 1 and then draw position 2. There is no harm in separating the problem and putting it into smaller parts as much as you can. And also, when I wanted to analyze the forces, I draw free body diagram at 1, at 2. It's difficult to look at the distances, so instead I chose a reference and I looked at the distances between the point of the force and the reference in both locations to subtract them. With this, I will conclude this module. I hope that it was useful to you and that you enjoyed it, and I wish you the best of luck with your studies. Thank you for listening.